All right, so we have just gotten done talking about chemical bonding, and we utilized our particular uh, electron configuration to explain why and how atoms chemically bond. Remember, the overall goal is for them to be chemically stable, and to be chemically stable, you have to have a complete electron configuration that matches that of a noble gas. Okay, the reason why is it fills that outer energy level s and p subshells. Okay, so we start out here with the atom, and we're going to get into trends, but we first must understand a couple things about the atom. Most of the volume, and we've talked about this before, most of the volume is determined by the electron, the movement of that electron. So this red cloud that you see in this picture here, that is the radius of our atom, which is how we measure its size, and it's measured in this unit called angstrom. So we're 1 times 10 to the negative 10th meters if you're looking at that. Okay, very, very small. Now, first statement here says atoms of different elements are not all the same size. Okay, so I want to go further than this. I want to ask why. Well, the answer is pretty simple, right? Every atom is going to have a different number of valence electrons, and because of that, they're going to occupy different numbers of energy levels. And so we change here our mindset to go from talking about radius, which we'll talk about quite a bit here, and we have this. I want you to think about, just for a second, all of these ions. What do they have in common? Well, the answer is this. They all have the same electron configuration. Okay, so they have that same electron configuration, and that electron configuration is as follows. That electron configuration is 1s2, 2s2, and 2p6. All 6 of these atoms are going to have the same electron configuration. Now we ask ourselves, okay, well, of these, what is going to have the largest radius? Well, nitrogen, the nitrogen ion, nitride, in with a 3- charge, has the largest radius because the most electrons have been added to that particular atom. Now, the smallest ion here is aluminum because that has the most electrons taken away or removed from it. And it's the aluminum ion with a 3+ charge. Now, what we call these items up here, these ions, is an isoelectronic series. And so an isoelectronic series is just saying, hey, a set of atoms, ions, or molecules are all going to have the same number of electrons. They're all going to have the same electron configuration, which is the case that we have up here. Okay, so now that we know a little bit about our particular radius and have identified a few things, we can move on to our trends. Okay, the first one we start here is this of chemical periodicity. Okay, based on the periodic table. Again, they've set the periodic table up very, very well. And as a result, there are several trends that we'll look at. Okay, so from left to right, something happens. From top to bottom in the periodic table, something happens. Okay, almost all of these can have some type of reasoning based upon that electron configuration and the number of valence electrons in that particular atom or ion. All right, we're going to look at a total of 5 different properties. Okay, so the first property is atomic radii, okay, or radius. Okay, radius is just measuring the size or the volume of that particular atom. We saw a great picture of that at the beginning of today's notes. All right, here we go. Trends. All right, you need to know these trends, and you need to know the general definition here of what the atomic radii is. Okay, as we go down in one single group, that's the up and down column, the radius increases. As we move from left to right in one single period, the radius decreases. Okay, again, you need to know that, but we also need to have some understanding of why this is occurring. Okay, so let's take this one trend at a time. Okay, let's start with moving down a group. In that previous slide here, I stated that the atomic radius increases and the question should be why? Okay, why is that occurring? We have to look at the atomic structure to fully answer this particular question. Okay, well, let's do this. Let's look at group number 1, and let's look at 3 elements, and we're going to identify their particular electron configuration. We're going to look at lithium, we're going to look at sodium, and we're going to look at potassium. And if I list these electron configurations out, lithium would have the electron configuration of 1s2, 2s1. Sodium would have the electron configuration of 1s2, 2s2, 2p6, 3s1. Potassium would have the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Now, all of these have one valence electron, right? This was what makes them a family, or what makes them involved in a group. But I want to point out one thing. Yes, all of these things, if we would highlight, again, have one valence electron. However, as we move down our group, the number of energy levels is increasing. Well, as we add energy levels, think of it as adding layers, right? As you add more and more layers, our radius or our size of our atom is going to increase. Now, let's look at our second trend that was listed just before, and that is left to right through one period, across one period, your atomic radius is decreasing. And the question once more should be, why is this occurring? So once again, let's turn to our electron configuration, and let's start out here, period number 2, the first element in period number 2, lithium. Again, has the electron configuration of 1s2, 2s1. And let's go almost across period number 2, and let's stop at fluorine, okay? Our fluorine is going to have the electron configuration of 1s2, 2s2, 2p5. Now, we have this to keep in mind. Lithium, in this scenario, has 3 protons, and because it's neutrally charged, it hasn't had any electrons added or taken away from it, it has 3 electrons. Fluorine, remember these are atoms, not ions, has 9 protons, and it's neutrally charged here. It has 9 electrons, okay? Now, we also need to keep in mind this point right here, and that is opposite charges are going to attract. Okay, that means protons, positive protons, are going to attract those negative electrons, okay? Now, I want to look here specifically at fluorine, okay? So fluorine, we have this occurring right here with the fluorine. 9 protons is a lot more protons than 3 protons, okay? There are more protons and more electrons. I'm going to make that point first. So you may be thinking, okay, just above we said, hey, we add more, we get a bigger radius. Why does fluorine have a smaller radius? Well, here's this. With more protons, you are going to have a more attractive force. As a result, it's going to cause the electron to be pulled even closer. Because those electrons are pulled and they're pulled closer to the center, to the nucleus, it is going to decrease the atomic radius. Now, this is a pretty good explanation, but I want to make one important point here. Okay, we really talked about, okay, more protons, more pulling power. That's why as we move left to right, the radius actually decreases. As we move top to bottom in a group, our energy levels are added, and so that increases the radius. But we're missing a point here that I'm not going to talk about today, and that is this. To fully explain this, we would have to talk about the concept of nuclear shielding. And again, I'm going to leave that for another day when we have a more focused set of notes there. Okay, but this gives us a pretty good idea, pretty good explanation of why we have our radius increasing top to bottom and decreasing left to right in a period. Okay, so let's go on and let's keep talking about our trends. All right, got a couple of different pictures here of our tables here. You can see the size. This is nice. It's a periodic table of our main group or representative elements here. You can see the size from top to bottom increases, left to right will decrease in that period. We also have a chart here that shows the actual radius. These are measured in angstroms. Again, just the unit that they utilize for measuring that radius. And again, left to right is going to decrease. Top to bottom is going to increase. Yeah, there's some weirdisms happening with the transition metals. Remember, we have that D block or D set of electrons, which is causing that. Okay, ionic radius. Remember, to be an ion, you either have to lose your electron, become positive, or gain electron, become negative. Okay, so a couple of important things here with this. Cations are smaller, anions are larger. All right, well, let's just put it into simple terms here, and that is this, right? If we talk about our cations, the cation of sodium ions, Na plus, Na with a 1 plus, is going to be smaller than its sodium atom. Ion, positive ion, smaller than the atom itself. Now, just the opposite is true for something that we have on the right-hand side, the negative side here, and that is this. Your fluoride ion, F with a 1 minus charge, is going to be actually larger than the fluoride atom. Okay, now let's take a little bit of time to explain why this is. So the first thing that I want to talk about here is this. I want to talk about why are cations smaller than their corresponding atoms. Well, again, let's go ahead and let's utilize our electron configuration and let's do some comparison. And that comparison is simply going to be with lithium here. Lithium atom, not charged, is going to have the electron configuration 1s2, 2s1, whereas the lithium ion with a 1 plus charge here simply is going to have the electron configuration of 1s2. All right. Well, here comes our first important point to explain why this is. The lithium ion, the positive ion here, is going to have a smaller or less number of energy levels in this particular cation form. So it would be like wearing a coat on a cold day, going inside, shedding that coat. Well, you've lost an electron, you've lost the coat. As a result, your overall size or the radius size is going to be smaller. Okay. Now, our second point that I want to make here is why are anions, the negatively charged ions, larger than their corresponding atoms? And again, we're going to do some comparison here. If we look at the fluorine atom, it's going to have the electron configuration 1s2, 2s2, and 2p5. Now, we add one additional electron and we get the fluoride ion with a 1 minus charge, and it's going to have the electron configuration 1s2, 2s2, 2p6. Okay? Here we have a unique circumstance here. Okay? With this scenario, we actually are still containing the same number of energy levels. So you might be wondering, okay, well, what really is our explanation for why this ion is actually larger than its corresponding uncharged ion here? And here is our key point here. The fluoride ion is going to have one more electron. And with our fluorine having one additional electron here, that 2p6 instead of 2p5, the electrons in all of this scenario and all of the atoms are going to have the same charge, and we have to remember that like charges repel. So to put this all together, to put it all in perspective here, to explain this is this, right? Our big major component, our like charges are repelling, and so that leaves with this statement here. As our electron expands outward, because they're repelling, right? They're moving away from each other. They are doing this to minimize that repulsion. And so as a result, the ion in this case, to reduce that repulsion, is going to cause the radius to get bigger. Okay, so we add an electron, we add more negative charge. We got to reduce the repulsion, so the ion in this case is going to expand outward. All right. So we got through our big ones here. Again, we'll look at our chart here. This shows you what the radius of your positive ions, remember they're smaller than the atoms, then your negative ions on the right-hand side here are larger than your corresponding atoms. Okay. Now, I like this photo here because it shows the comparison between the atom and the charged ion. And you can compare and see the difference, and everything that we just talked about can be applied to that picture there. Okay, so now we'll move into a few additional properties here, and we start here with ionization energy. Ionization energy, and again, we need to know the definitions here of all these trends, is the ability or the amount of energy to yank an electron from this gaseous state. Gaseous state just gives us a way to calculate, measure those particular energies. Okay, here we go down to this. Large ionization, really, really hard to remove an electron. That atom wants to hold on to it, does not want to get rid of it. Small ionization energy, easy to remove. For the most part, that atom wants that electron gone. Noble gases, largest ionization energy levels. Remember, they're happy. They have that complete electron configuration. Alkali, group number 1, metals, are going to have the smallest ionization energy. Okay, transition metals going to have very similar. We'll talk about why that is. Okay, so now let's explain these 3 particular trends. Okay, so trend number 1. Why do the noble gases have really large ionization energies in each of those periods? Well, let's think about this, all right? And let's turn back to electron configuration, and let's look at the electron configuration of neon in period number 2. Electron configuration would be 1s2, 2s2, 2p6, okay? And in the case with ionization energy, we lose 1 valence electron. Now, all of a sudden, our electron configuration is this: 1s2, 2s2, and we have 2p5. Well, this would form a neon ion with a 1+ charge there. And by doing this, by losing just 1 valence electron, we have now lost the noble gas electron configuration. at this point in time, because we've lost our noble gas electron configuration, the atom is no longer stable, right? And so if it's not stable, if it's not atomically stable, it's not in the right state, it's going to need to obtain that electron back. So this is why they just don't give it away, right? Because they're in that happy mode, they're in that happy status right there, okay? As a result, neon and all other noble gases make it as difficult as possible to lose a valence electron. So now we move on to our next point here. And I'm going to get rid of this info and make our next point. And our next point is this. Why do the members of group number 1, okay, your alkali metals, why do they have the smallest ionization energy? Well, again, let's look at our electron configuration, and we're going to start here with sodium. Sodium has the electron configuration of 1s2, 2s2, 2p6, and 3s1. Well, if it loses just one valence electron, it's going to have a resulting electron configuration of 1s2, 2s2, 2p6. Okay, well, remember this would be classified now as a sodium ion with that 1+ charge. And then by losing this, sodium has obtained that noble gas electron configuration. Well, that has made the now ion atomically stable, and it's satisfied that need there. It's satisfied the desire to be structurally sound. Okay. Now, my last point here is this, and I'm going to delete this and make it my last point with this. Our transition metals, why do they have pretty similar ionization energies? Okay, and so we're going to look again at our electron configuration. Well, let's look at 3 transition metals, okay? Let's look at titanium. Let's look at manganese. And let's look at nickel. And I'll put up the electron configurations here. Titanium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d2. Manganese has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Nickel, electron configuration of 1s2, 2s2, 2p, 2p6, 3s2, 3p6, 4s2, and 3d8. Well, I want to highlight this and see if you can catch on here. The valence electrons, okay, are in the 4th energy level. Now, in this scenario, if we lose one valence electron from any of these, we'll be losing the same type of electron from the 4s sublevel. And that will take about the same energy. All right, so that's a pretty good stopping point right here. We'll pick this up with trends number 4 and 5 that we will discuss in a later part of this day of video.